Hi, everyone. It's so nice to see you all. My name is Molly Larkin. I am with Fourth Brain. We are an AI education company. We run workshops, events, talks, all focused on helping you grow your career in AI. I'd like to introduce our two presenters today, Laura Funderburk and Sina Rafati. Laura is a developer advocate at Bytewax, and Sina is an artificial intelligence architect in the aerospace industry and is also an entrepreneur in applied research in different AI domains. I'm going to let them take it away. There will be some slides. There will be a notebook that I will share at the end. Please let us know where you're calling in from in the chat. Put any questions you have in the chat. We will address them either in the moment or we will address them all at the end. All right. Sina and Laura, take it away and let me know when you're ready for your slides.
Thank you, Molly. Yep, sharing my screen. Okay, I assume my screen is visible. Can I get some confirmation?
Yep, it looks great.
Oh, awesome, cool. Okay, thanks a lot, Molly. So we just skip over the intros. Okay, so have you ever bored to that level that you have nothing to do on Earth except going to kitchen, open the fridge door, take a glance of what you have, and all of a sudden you decide you don't want anything, just close it and head back to your work? Not that I'm suffering from ADHD, but we have all done that, right? So let's imagine that you have an AI assistant that can take a look at your fridge, and you can simply ask it, based on the materials that I have, do you have any suggestion for what I can cook and enjoy? And the assistant comes back with a series of recommendation based on the materials that you have. And let's play dumb and assume that we don't know how to make a orange juice a smoothie. We just ask, okay, I want to try orange juice a smoothie. Would you mind providing me the full recipe? And your assistant just provide you all the ingredients and the detailed instruction of how you can make it. So now we can kind of step it up. You can imagine that we can bring another modality like audio and mention and basically talk with your fridge that I need something to change my mood, and your fridge knows your personal behavior, and your fridge understand your current mode, and then it will suggest you kind of a material that you can enjoy. So putting that fun kind of application aside, one of the key requirements in a lot of LLM or VLM based models is the capability to digest information. And we know that a lot of materials are not generated through basically text generation softwares like Word or LaTeX. They might come through scan documents. So VLMs can be leveraged to do the optical character recognition. Not that we are promoting our workshop for coming multimodal foundation models, but imagine that we have a banner and you want to know that what is this screenshot about, what would be the appropriate audience to attend such a workshop. So the idea is that when we have a mixture of vision data and text data, we can leverage vision language model to digest information and use that for any downstream application. So putting all the other modality aside, our focus today is just vision language model, which are a system that can process both images and the text. So you can imagine that we can have a dual way communication. We can go from text input to the images, like generation of synthetic images through DALL-E or Midjourney, or in the reverse, that you have an image and you want to generate captioning and provide basically what's the image about, including GPT-4 or LLaVA. So there are different categories of leveraging vision language model. We can leverage them for visual question and answering, meaning that you provide an image and you start communicating with the image through your assistant, provide the question, and the assistant has an understanding of a visual scene, and it will provide you context about the question that you asked. Or you can have a simply a visual dialogue as a friend with your assistant about watching a movie or observing an image. Visual and language model can also be utilized for image captioning, that you can generate what is the description of the image and use it for any downstream application. And these days we can also use it for image classification or even object detection, that you provide the text prompt and you're looking for an object that you're interested. Putting these kind of intro aside, let's dive into the LLaVA. That's why we are gathered here. So in order to understand what is LLaVA, first we need to understand how it was trained. So the way that LLaVA was trained was leveraging visual instruction tuning. The idea is that we need to have some series of instruction tuned data sets so we can leverage it for vision language model training. So now how we can get that visual instruction tuning data set. So the original authors, what they have done, they have grabbed a COCO dataset, which we are all familiar, which has a series of caption for per each image. And let's combine that with the vision data that is coming through the object detection. On top right, we can see that we have the captions coming from the data set, and we also include the bounding box of the object that is unidentified. Now, this information was injected into a LLM model, in this case, a GPT-4, and there was categories of communication was put together to generate instruction tuning dataset. The first one was conversation, meaning that we provided the image and the context through the the caption, and there are a series of question and answer was injected into the LLM. For instance, in this specific example, what were the type of the vehicle which is featured in an image? And the assistant, LLM assistant, basically get back and provide the text answer to the question. And then the category of the communication was through the detailed description. And given the caption and the image, or the LLM was tasked to generate the detailed description of what is inside the image. And the third category was the complex reasoning. So for instance, in this example, there are series of people kind of standing around the largest UV with their baggage laying around. Probably they're kind of struggle with how they can fit their baggages into the car. So mixture of these conversation, detailed description, and complex reasoning was injected as an instruction tuning for training of LLaVA. So the original authors used 158K language image instruction, which included 58K conversation, 23K digital description, and 77K complex reasoning. So now having that data set, what is LLaVA and how is basically trained? So on the right, we can see that the objective is that we want to bring the context from the text input, language instruction, and the image input to be aligned together. So what's happening is that the image goes through the vision encoder, and that get aligned with the embedding that is generated through the embedding generation of the language input. And the objective is to not touch the vision encoder itself. So for that reason, a projection layer was injected, and that was basically fine-tuned to align the embedding of the vision input and the text input, and they pass through another language model to provide the output according to the instruction that is provided. You can see on the bottom right the context and how the system message was being injected, that there is a chat between human and AI, which can provide helpful and detailed answers to the human questions. The way that the system was designed is to provide the system message, break it out by the end stop token, the instruction coming from the human, and then assistant provide the answer. So the objective was to use this instruction to do the fine tuning of the model, and especially the projection. So the input can be random selection of pair of question and the image input, or the other way around. So you provide the image then and provide the instruction. for the first time that you're kind of having communication with that image, and anything down the road, you just provide the question. And all the fine tuning happens on just the assistant response, which is in this case shown as X1A and X2A. So to put it kind of in a nutshell, the objective of training was to design a projection layer that can align the vision encoder embedding with the text embedding, and then pass it through another language model to provide the output to the instruction provider. So you don't want to go that much into the details of the performance. There's a lot of materials out there that you can dive into it, but there is a one that we want to touch on. So there was a basically research paper that what they have done is that they have kind of investigated what is the range of the performance with different instruction tuning. On bottom table, you can see that what they were doing is that they were kind of comparing the output of LLaVA against GPT-4. And if they were using the full data, meaning that they had all three categories, a detailed description, complex reasoning, and a question and answer, overall they had the performance of 85.1, which is a bit lower than a GPT-4. The interesting thing is that regarding the complex reasoning, LLaVA actually was performing pretty good, around 96.5%. But another important aspect of this is that, as you can see, as the data was basically being removed, the instruction tuning was being removed, the overall performance was dropping from 85.1 down to 21.5, which indicates the importance of instructional tuning for LLaVA. So now our goal today is to do the fine tuning, but we know the overall process is that always, in order to bring a foundation model to life, we can always start with the prompt engineering. So if that doesn't work or it doesn't have the performance that we are looking for, then we will step it up and we go to the pre-training. And if that, we go to the fine tuning, and if it doesn't fit the purpose and the performance that we are looking for, then we go for full pre-training. So what we want to leverage today for fine-tuning LLaVA is the so-called transformer reinforcement learning, TRL, which is a technique that combines the strength and power of transformers and reinforcement learning together. So behind the scene, transformers are being used to understand the current situation of an agent and its surrounding, which helps the agent to have a smarter choice and learn through trial and error. So you can imagine TRL to be like a tutor that can decompose your learning and provide you a smaller, basically task, and it will provide you personalized feedback. The reason is that due to the attention mechanism that we have in Transformer, we can help the agent to focus on the errors and to improve on those. So overall, the architecture of transformer reinforcement learning is that there is an encoder which processes sequence of state and actions, and there is a decoder that generates future action based on past ones. And there is also a value network that estimates the rewards for certain action, helping the decision to be made. So thankfully, there are a lot of these stuff is already being implemented. So Hugging Face provided the packages and modules that also integrated transformers, which is what we are going to use, and we will demo it today. And for those of you who are not kind of familiar with LORA, there is another fine-tuning technique that we are leveraging, which is basically a parameter efficient tuning, a low-rank adaptation. The idea is that when we are dealing with kind of foundation models, the number of parameters that we are dealing with is pretty large. Meaning that if you want to do the fine tuning or training, it will require a huge amount of computation. But on top of that, it has the capability to hit the catastrophic forgetting. Because if we start to bring the pre-trained weights to be updated through our, a small data set, we might basically lose the performance of the original model. Instead, what is offered to do is that we bring a new module or new network injected into the our foundation model. And instead of having full representation, let's say in this case, we have a n by n matrix, we represent that matrix as a multiplication of two lower rank matrices. So instead of having n by n matrix, we just represent that as a n by r times r by n matrix. There are two benefits of doing that. So the first one is that the total number of parameters are getting dropped significantly because we are dealing with many, basically much lower number of parameters. And also that will save a computational cost. So you can imagine the smaller is our lower rank, basically representation, the faster will be the processing. Obviously, that comes at the expense of having lower performance. So it's always a balance of getting higher performance versus computational cost and the requirement of the data. So another benefit of using LoRa is that we can have a different LoRa adapter for different purposes. So you can basically keep your pre-trained weights for your foundation model as is, and you bring a LoRa adapter for a specific task, for instance, image captioning or image generation. So in that case, when you want to have a mixture of basically tasks, you bring that appropriate LoRa adapter, and that will help you to not touch your main pre-trained weight and bring different LoRa adapter for different tasks. Again, we are using the implementation in Hugging Face, and the main three parameters that we will target to use for our LoRa adaptation, low rank adaptation, is the basically rank of the matrices that we have R, and also the target modules. The target modules is basically what modules inside our whole infrastructure we want to basically represent with lower rank. For instance, if you are dealing with all linear layers, we want to just basically represent those all linear layers with the lower rank. And also the alpha parameter for LoRa scaling. Okay, so having said that, so we want to go through kind of the process that we put together and the data set that we pulled from Hugging Face, and show you how we are leveraging all these techniques to do fine-tuning of LLaVA. I will pass it to you, Laura.
Thank you so much, Sina. So for today, I think we had a chance to understand a little bit more about the theory behind how fine-tuning works and how some of these model architectures work. But obviously, a lot of you might also have interest in how to get access to these models and how to get access to these technologies so that you can start working with them. So today I'm going to be sharing with you some resources, and I'm going to be walking you through some of the basics, for how to get started playing with these kinds of technologies. So there's two things to keep in mind in here when we interact with these models. There's a few key pieces of knowledge to take into account. One is where we are accessing the models from. For today's demo, and if you're interested in pursuing the next iteration of this workshop, we're going to be working with open models from Hugging Face. What's really nice about working with these models is typically when you get access to the language model or the vision model through something like Hugging Face, we typically work with a Python package called transformers. And Hugging Face has created quite a bit of Python packaging around technology that allows you not just to access the model and the model weights, but also allow you to fine tune using LoRa or training reinforcement learning, which we showed today. So I'm going to go ahead and share with you how you can get started exploring some of these models. So first things first, I want to walk you through Hugging Face a little bit. So if we, Justina, can you do a confirmation that you can see my screen?
Yes.
Okay, perfect. So within Hugging Face, now I'm just going to go back and go to the main page. So within Hugging Face, we have the option to search for models in here. And so in here, what's really key for us to access a model is this idea of the model card or the model ID. Typically, the format that this follows, and I'll just do a little bit of a zoom in, is the provider. This is like the group, and followed by the card. So we're going to be taking a look at two different models in this notebook. So we have the Meta Llama 3, 8 billion parameters, and then the other one is LLaVA, 1.57 billion. So through these model cards, you can simply get it by visiting huggingface.co/lava-hf. This is the name of the group, and then here's the model name. If you're interested in finding different models, of course, you can visit different organizations. This is the organization for the LLaVA Hugging Face. And then in this case, we're working with LLaVA, the visual instruction tune version of Llama, which allows you to do some more visual recognition tasks. Within the space, you can take a look at the different models that they look at. So today we're going to be working with this LLaVA 1.57 billion. And in here in the model card, you have a Google Colab where you can start interacting with their models. You have some details about the model, how to use it. And then this is a piece that's important. Within the Jupyter Notebook, we're going to be using some of this code. So within the Transformers library, we're going to be using this pipeline functionality to extract or to go from image to text. And the format we will follow is we have our model ID, we have the pipeline, and then we have some kind of image that we can do. So within this kind of configuration, we can access the model weights, fine tune, etc. The other thing, of course, when it comes to fine tuning is there is no fine tuning without a data set. So for the purpose of this notebook, we're going to be working with this LLaVA Instruct Mixed. So if we take a look at the data set in here, I have these two attributes. I have the messages and I have an image. And in this case, I have a JSON object, or maybe a list of JSON objects that tell me the content. In this case, I have some indices, some text, and the role, and then I have an image. So the goal for us in this notebook is going to be to fine-tune LLaVA using the techniques introduced in the topic to fine-tune it on this very specific data set. I'm going to go ahead and jump into the notebook. And so there's quite a bit of content in this notebook, so we won't really get a chance to go too much in depth, and the notebook will be made available at the end of the session so you can explore it in your own time. But for the purpose of showing you a big level overview for how it works, I'll just go through the notebook quite quickly. So I'll zoom in a bit. So within this notebook, we have two modalities. One, we can load the model in full. If I go to the very top in here. So in here, I can download a language model using the Transformers library. So first I would go ahead and do an installation through pip. If you've worked with Python and pip before, it's very straightforward. And then from here, for me to access the model, I can go ahead and set up my device. In this case, we're going to be working with a CPU device. For fine-tuning, I do want to give a heads up that it is highly recommended, or in some cases even necessary, to have GPU runtime enabled. I believe Google Colab doesn't enable this for free. You'd have to get a pro account. So if you are interested in fine-tuning a model using either LORA or using reinforcement learning, then I recommend, if you don't have a strong GPU on your local computer, you can always go to Google Colab and get a pro account and then pick a runtime here. If I go to change runtime, I can pick different options in terms of how much GPU power I need. Once we download the model, so essentially what's going to happen is once I download the information through this card information, I will go ahead and obtain the model shards. And then in here, I have information, or I have basically the weights of the model right in my computer. Now, one of the things that you'll notice here is it is a bit heavy, and it is quite intensive to do it this way. So you have the option to download the model SS. The second option that we are giving you is to download the 4 bits quantized version of the model. This makes fine-tuning a lot easier because we're dealing with a much smaller version of the model. So it's quantization along with something like parameter efficient fine-tuning are both techniques that allow me to fine-tune my model in a much more efficient way. So within the code, we have our installation. And then from here, to access a vision model such as LLaVA, we simply need to pass the ID of the model. So again, if I go back here, I simply get this by copying this LLaVA HF, LLaVA 1.57 billion, and then from here I can start initializing the process of accessing the model weights through the quantization configuration. Some of the other things that you can explore as part of this notebook is we have the creation of these prompt templates. So I'm going to go ahead and break down what is going on in here. So in here, remember, we have our data set. Our data set consists of these JSON objects that contain assistant role content. So in this case, I have questions like how many travelers from Asia were in the US in 2020? And can you extract the full data and reformat it as a markdown table? So we're going to have these images and some questions from the user. And the idea for the model is to be able to, or for us to be able to adapt the model's behavior so that when it receives an image as an input along with an instruction, the model can successfully return the information that is desired. So the way we do this is through this template. So in this template, I have a mix of text and also some Jinja formatting. This allows me to iterate. So in this case, I have a chat between a curious user and an AI assistant. The assistant's goal is to give helpful, detailed, and polite answers to the user's question. And then in here, we're going to go ahead and iterate. So in this case, we're iterating through all the messages in the messages object. If the role of the message of if the role of the AI assistant is user. So in this case, we're looking for the user query. And then otherwise, if it's not a user role, then we're going to go ahead and assume it is an assistant role. And this goes back to this idea of how we interact with some of these models. If we think about, for example, about how we interact with an LLM from something like OpenAI, if you have ever had a chance to interact with their OpenAI API, you would have noticed that we have these roles. We have the assistant role, we have the user role, and we have the system role. So it's going to be very similar in this case, where with the system role, we're sort of giving a high-level overview of the instruction that we want to resolve. The assistant is in charge of providing that result, and then the user would be someone like you and I who goes to the model and asks for something. So this follows a very similar format. So in this case, my goal is to iterate through each and every one of these entries and identify whether this was a user question or an assistant question. In this case, these ones are quite varied. So in this case, we have an assistant entry. So first we have to categorize whether we're dealing with a user or assistant. And then from there, the other thing that we're doing is, now that we've identified the type of role, next we iterate on whether we're dealing with the kind of content. So we have content that might be of type text or content that might be of type image. And we treat each accordingly. And then at the end of this, we simply finish iterating through these. So if you haven't seen one of these templates before, don't worry. All we're doing is just we're providing the model with an instruction. And this Jinja formatting is allowing us to iterate through the content of our data set or our documents. From here, once we've had a chance to load the model from Hugging Face onto our system, and we have our LLaVA chat template, the next thing is for us to tokenize it. And if you haven't had a chance to learn about this idea of tokenization, essentially what we're doing is we're going to be taking a chunk of text, and then we're going to split it into smaller pieces. Tokenization is one of the key strategies or building blocks of dealing with text when it comes to transformer architectures, and it allows the model to start receiving the information. Remember that an LLM or one of these language models, typically what their aim is to predict the next token based off of the previous tokens that it has received. So this idea of tokens is very, very important. So we're going to go ahead and tokenize our chat template. And then from here, the next thing we could do is to create our data collator. So in this case, we can iterate through our data examples. We apply the tokenization, and then from here, we can initialize it. Now, once we have enough machinery in place to process the data, we can now load the data set. And as before, Hugging Face provides, just as they provide the transformers library that enable us to access the models through this card, Hugging Face also provides us with this datasets library that allows us to load datasets from Hugging Face. So this is a data set that we're using to fine-tune the model. And we have here the card. So it's going to be the same idea. I'm just going to go ahead and use the load datasets function from the datasets module. I can go ahead and then extract download the data set into my computer using the ID. And then from here, we have two subsets. We have the testing one and the training one. And this follows a very similar pattern or idea as to when I'm fine-tuning a model in classic machine learning, where I have my training test and my testing data. I'm going to go ahead and train my model on the training data set. And then I have reserved a test data set with the correct answers. And I'm going to go ahead and compare the predictions or the answers that the model is given. When the model is given partial information, I'm going to compare that against the test data and see how well the model performs. So it's a very, very similar idea to some of these classical ML fine-tuning. From here, I can do things like saving my data sets to disk if I wanted to save these locally. And then here's where stuff gets interesting. So for us, maybe this is where things get a little bit different between fine-tuning classic ML models and fine-tuning something like a language or language and vision model. So first I have my output directory, the learning rate. These kinds of numbers or values, these ones are typically determined by the characteristics of the model. So you can get more information about how to get these from the papers. So if you go back to the LLaVA model card, typically you can find information on, let's say there's a paper in here or resources. So if you have any questions about what type of parameters to pick or what is the best possible set of parameters for your model, I highly recommend that you visit the resource, take a look at the paper and find out. Typically, you can find much more in-depth information on the architecture of the model and the types of parameters that make the most sense. In this case, these were determined based off of some of the architectural format of the model. And then from here, we can set the low ranking adaptation configuration. So remember, in this case, the idea of using LORA is we want to make sure that we're fine-tuning our models in an efficient way. Again, with these models, we're dealing with billions of neurons and a lot of layers. So determining which layers or which nodes to go ahead and fine-tune can be highly expensive from a computational point of view. So the idea of LORA and parameter efficient fine-tuning is to give you an efficient way to fine-tune the weights while retaining quality and functionality of the model without needing to go into too much expense when it comes to fine-tuning. Of course, the biggest expense when it comes to fine-tuning is GPU usage, which we know is not a free resource. So this idea of LORA and parameter efficient fine-tuning became highly popularized in the last year and a half as a technique to fine-tune not just large language models, but also vision models with a language component to them. So as before, we would set up our LORA configuration. Again, if these values don't make sense, you're wondering, oh, where can I get these values? Where can I pick? Remember, going back to the basics understanding, we've added here a resource where you can read a little bit more about LORA, where we're picking things like 64 and 16. I'd recommend to go there. And then from here, we can provide our trainer with our training data set, our evaluation data set, and our LORA configuration. And then from here, we can simply train. So I didn't run it during the demo for the purpose of saving you time. Some of these processes can take quite a bit of time, a few minutes, all the way to maybe, I don't know, half an hour, an hour. So, but the point is to give you this resource and for you to play with it. The last thing I want to show before we move on into the next phase is this idea of pushing the model to the Hugging Face hub. So one of the things that's really neat about working with models from Hugging Face is, I can download my model, or I can download the weights for a model. In this case, we worked with LLaVA. And I can also go ahead and download this data set, and I can fine-tune my own data set, my own model with the data set, evaluate my results. And then let's say that I spent a lot of time, maybe not with this data set, but I spent a lot of time curating a newer data set, and I have a model that has gotten very good at one specific thing. For example, maybe I fine-tune my model so that it is exceptionally good at extracting numbers from pictures of tables. Maybe that was how I fine-tuned my model. So if you get to a point where you have fine-tuned a model and you would like others to use it, Hugging Face gives you the option to push to the hub. For pushing to the hub, only thing to keep in mind is we want to make sure that we create tokens. So if I go here to settings and I go to access tokens, you have the option to generate tokens for writing and for reading. You will need a write token to push your fine-tuned model onto Hugging Face. And then if you want to read other people's models, you just need a read token. But once you have this token, you provide it in your environment. And then from there, you can push a model to the community, and then others can use it. You won't have a nice card like these ones. You'll have to spend a little bit more time. But it is one of those things that I think make this idea of sharing models highly valued. One final point I want to touch on before passing it back to Sina is we've been talking about when to do fine tuning, when to do training from scratch, and then also when to simply use another person's model and simply prompt it. So one good thing to keep in mind when choosing which route to go to, as some of these fine-tuning tasks can be quite expensive, is to first identify what type of task you have, whether it's a classification task, it's a generative task, or it's a, I think those are the two main ones that I can think of. Try to think about the model architecture. There are certain models that are better suited for classification tasks. There's models that are better suited for prediction tasks. And by prediction, I mean generation. Like if I want my model to generate new content as opposed to simply classifying based on the information that I give it, having a good familiarity for the type of architecture that you're dealing with is good. So in this case, if I'm talking about something like Llama and LLaVA, both of these are models that are good at generating tasks as they follow a very similar architecture as GPT. If you wanted to deal with something more like classification, maybe something going for something like a T5 fine-tuned model might be a better choice. Another thing to keep in mind is fine-tuning, of course, is expensive, not just because of GPU usage, but good fine-tuning requires us to spend quite a bit of time curating a good data set, which is, I think that also is very expensive. So before venturing on to fine-tuning as your task, I would encourage you to first evaluate what is the task that you have at hand. Are there models out there that already perform that task? And can you try to do something like retrieval augmented generation instead of fine-tuning, or just prompting to get the model to do what you want? And if the answer is no, only then go to this idea of fine-tuning, spend some time curating a good data set, and then go for techniques like LORA, parameter efficient fine-tuning, and reinforcement learning. So I think those are my key takeaways from the notebook. What I really wanted to show you is, even though these techniques are can seem a little bit advanced, there is a lot of machinery in place today so that you can access these tools and start fine-tuning using Python and the open source ecosystem. So I think with this, I'll pass it over to Sina, and we can start addressing questions as well.
Okay, thanks, Laura. Yeah, maybe just one thing to add. I think, as Laura mentioned, the key kind of takeaway is that going through the process. So always start with prompt engineering, then go through retrieval augmentation, and then start dealing with the fine tuning and full pre-training. Because the reality is that the more you push to the right regarding the complexity, you need more data and obviously more money to buy the GPUs. But with that being said, we just want to wrap it up and kind of open the floor for the questions.
Thank you both so much for that. Yeah, we do have some questions coming in. I think I'm going to work backwards through the questions. So if either of you want to reshare your screen at any point, just throw it up there. So Vignesh asked, can you explain the templating? And wouldn't a data point for training be a single text image pair within the prompt? So I think this is related to the notebook that you did, Laura.
So if I'm just going to go back to the code again. Share screen, LLaVA fine tuning. So if I go back to this Jinja, so in here, notice that we have this for loop. So we're iterating through all of the messages in this case. It wouldn't be a single data point, but rather when the model receives this and receives the data set, the model will have implicitly access to all of the content or all of the entries in the data set. What this Jinja templating is doing is it is essentially allowing a mechanism for the model to access all of the data points. And in this case, even to categorize whether they're a type the type of role user or the type of role assistant, and whether the entry or the content is of type text or of type image. So through this Jinja templating, we're essentially iterating and giving the model access to all of the entries in the data set, not just one.
Great. Thanks for addressing that. And Vignesh, if you need any more details, please just write in again. Let's jump to this one. Can we use custom data sets? What is the data set format supposed to be like?
Yeah, I mean, the objective is that, well, first of all, we can always go back to the way that the LLaVA originally was being trained, generate your visual instruction tuning data set. But another good source is basically the already pre-generated data set that is in Hugging Face, which Laura was showing. That can be a good template to put together for your own data set. So the only thing that you need to put together is the really clean data, because since you're dealing with the fine tuning, you don't want to have any noisy data. So you need to provide your image and a JSON as a kind of Q&A between the user and assistant, and just put that together, and that will be your custom data set.
Great, thanks. Let's go to Brant. Have you done this with other versions of LLaVA? It seems that the model cards are missing to get some things working. Not sure.
So yeah, feel free to chime in, Laura. But the 1.6 at the beginning of the notebook, that was for demonstration of how to use LLaVA, basically using it for as a visual scene description. But the actual model that was used for pre-training, fine-tuning, was basically 1.5 model. Laura, feel free to inject if you.
I haven't had a chance to do it with 1.6. In terms of the comment, it seems that the model cards are missing some files to get things working. That is unfortunately one of the pain points of working with open models, is that so sometimes, depending on who's maintaining the model card or who's maintaining the model, it's almost like trying out open source packages. You have a wide variety in terms of how well maintained the documentation is, how up to date the documentation is. So you might have some pip packages that are maintained by an organization where they're constantly pushing updates and they're constantly pushing new documentation. And then you might have also models that were fine-tuned by an individual or by a team that they just wanted to try it out once and see how it worked, and that they just pushed it out there with very little documentation. And so I think navigating this is one of the challenges of working with open models, and that I think there's so much variety out there in terms of the type of model you can get, where it was fine-tuned, and also the type of organization or group that pushed the model outside, that it is a common pain point, unfortunately. One of the things that I think has been very successful in the last few months is there are certain groups that started Dockerizing some of these models. I know that this was done for models like Llama and Mistral last year. I'm not sure if Dockerization of models has been done with LLaVA yet, but I would definitely encourage you to take a look at, not just through the Hugging Face, but investigate whether there's someone out there that packaged it so that it's ready to be used as is. Otherwise, you have to experiment with things like the version of the Transformers library, the version of the Bits and Bytes library, the version of any other dependency, and it's a little bit painful for sure.
That does sound painful. Great. Just continuing to work backwards. How much data is a must for fine tuning? It's a big question.
Maybe I will start, and Laura, feel free to add. I would combine the two questions, because I guess the same person also asked question about how we can use LLaVA fine tuning for multi-class classification of images. So the first thing that always we need to think is that what we are looking for, or what is the objective of our fine tuning, and does it worth to go through that process or not. So yes, behind the scene, we know that LLaVA is auto-regressive model. So in principle, we can bring prompts and generate the embeddings and go through the process of fine tuning to do the basic image classification. But the question is that are we willing to go through the expensive training of such a model? And also, we know that bringing these two together requires a huge amount of data. So it depends on the application, and I don't think there is a right answer about how much data is needed for fine tuning. Obviously, the more data that you have, assuming you have a clean data, because you cannot just push garbage data. At the end of the day, we know that any probabilistic model is garbage in, garbage out. So if you don't have enough good data, for sure, the output will not be reliable. Laura, if you want to add anything.
Yeah, I think in terms of how much data, I mean, I think a good benchmark is first assess. You can start with a smaller data set and assess how well the model performs. If the performance is poor, then increase at that point. How much? I don't know if you're asking the question in terms of millions of entries, or hundreds of entries, or thousands of entries. I think the how much data it takes for the model to perform to the way that you want is one of those very broad problems, because it depends, again, the model architecture, in addition to the kind of data that you're providing it, in addition to the type of task that you're aiming to resolve. So prior to, I think before answering the question, how much data should I give it, first answer these three questions. What is your task? What kind of architecture is better suited for your task? And is the model performant as is, or what kinds of things is it failing at that you're not happy with? If the model is failing at because it's let's say that it's hallucinating, let's say that it's saying or generating things that are wrong, then you might want to ground it through something like retrieval augmented generation. But if the model is failing, let's say because it requires access to a specific kind of vocabulary, let's say that you want your model to have a knowledge or understanding of specific words, abbreviations, or context that you couldn't give it through something like retrieval augmented generation, that at that point curating something like a data set for fine-tuning is the right way to do it. And again, I think because of how expensive this is in terms of GPU usage, I would start with a smaller data set, see whether that strategy is improving the results. And if it is, then maybe continue expanding onto that. And if it isn't, then I think at that point reevaluate whether a different model might work better.
Great. That's a great answer. All right, we've gotten a few more recently, so I'm just going to run through them. How does LLaVA perform with invoices? Any familiarity with that?
So yeah, I mean, maybe the challenge for the invoices is actually understanding the tables. So the objective is to go from basically table representation to something like Markdown that then we can inject it into our pipeline and then use it for interpretation or any RAG base. So there are tools out there that will help you to decompose your basically data coming into different categories, like you have image data, table data, text data, and then you can apply some fine-tuning to do the interpretation of those coming input. And so another challenge for the invoices, especially the ones that are not the standard, is the handwritten documents, right? So because people might put some handwritten notation or really weird notation that is dedicated to the invoices or abbreviation. So another challenge dealing with the invoices is having the understanding of how to interpret those type of data. But overall, short answer, yes, but it requires its own data set generation and process.
I don't have anything else to add to that.
Yeah.
That was a great answer.
We have a follow-up from Vignesh. Is a batch of training just a single iterated prompt with all the data?
Yes, that is correct.
Great. All right, let's try this one. How do you know how long to train the model?
That's classical. I mean, look at the losses, obviously kind of auditing the model after basically some fine tuning, because at the end of the day, you have your curated data set, so you can leverage that to not only do the loss calculation, but also some sort of human judgment to investigate what is the output and use that for fine tuning further.
Great. All right, we got a couple more. If you have any other questions, please put them in the chat, but here's one more for you two.
Is LORA to get into small IoTs?
How would you interpret this question?
Yeah, I know. But is LORA to get into small? How would you interpret it to get into?
Yeah, I think correct Correct me if I'm wrong. That's my interpretation of your question. So feel free to inject to the comment. But LoRa is to make the training efficient. If you're willing to bring your models to the basically IoTs, a smaller device that they don't have a processing power. Generally, what we are leveraging is quantization, because since we don't have that capability to do the full, let's say 32 point processing, that's where quantization come to the picture to make it ready for a small IoTs with a limited processing power.
Yeah, I think yeah, maybe what I understand from the question is that there might be conflating two things. So the other side to IoT, of course, is whether we want to get the model to receive information from devices and react to the information from devices, or maybe we're thinking about getting the model to send us an alert when there's a specific signal coming from a device. Let's just say, as an example, air quality. I want the model to send me a warning when, let's say, the particles in the air exceed a certain threshold, or let's say that I want the model to send me a warning when there's sighting of smoke or when ozone levels are high. So you can certainly fine tune or build a system for these kinds of systems. I think I would go back to what Sina said, that LoRa and parameter efficient fine tuning are more techniques to fine tune the model in a way that is computationally efficient while still retaining the quality of the model responses.
Great. Okay, I'm just going to keep going through them. There's a concept of LoRa stacking in image generation. Could you do something similar and train LLaVA for smaller specific purposes and stack multiple LoRas to make a more advanced multi-purpose?
Personally, I don't have the experience of stacking those personally in any application. So I'm not 100% sure what be the kind of caveats of doing that or what is the exact process. But based on what I have seen, it is possible to bring multi different models together and kind of injecting to help each other to do multi-purpose basically functionality. But bringing LoRa stack, personally, I haven't done it. Laura, do you have anything around that?
I don't have experience stacking. If I think about stacking, maybe what comes to mind is you want to fine tune different aspects or different behaviors of the model with data sets that are non-overlapping. I think that is one use case that I could see. I think at that point, if you wanted to do something like stacking, yeah, I mean, I would approach the problem by fine tuning in one area, evaluating, and then fine tuning in the other. I haven't had a chance to play with something like training or fine tuning parallelization, where you're training different aspects of the model at the same time with different data sets. So I think that is a very, very interesting question. I also haven't had a chance to explore. In terms of the functionality, again, I think the use case I would see is if you want to fine tune different aspects of the model where the data sets are non-overlapping.
Great. All right, I'm going to circle back to a question that came in very early. Can we fine tune LLaVA for multi-class classification of images?
I think we kind of addressed that while we were discussing the, let's say, how much data is enough, because that was coming from the same person. But yes, in principle, yes. But if you're dealing with just image classification, probably simple object detection might fit the purpose. The question to answer is that what you're looking for. Are you looking for searching objects from, text prompt? If that's the case, yeah, then yes, you can use LLaVA to search for your object of interest through text input. But if you're just planning to just do simple classification of images, probably going to the state of the art, something like YOLO might be a better approach than fine-tuning LLaVA.
Great.
Yes.
All right, we have one last question and then we'll wrap up. What type of model can you recommend to extract job skills from job ads?
I would say any text model
Yeah.
would do. I think you don't even need to do image classification or image extraction at this point. if you're new to extracting this with the model, I think, and if you're not too concerned about putting a little bit of money, I think GPT 3.5 Turbo has gotten quite cheap, and you can call their API, feed it either jobs in the form of an API response, or if you have a bunch of job postings and just in text format, I think any text-based model will do the job. If you're looking to, I think there is no fine tuning required for this type of task. You can just pull the model out of the box and then just use it. If you're wanting to use something like a little bit more open, I think Mistral has reached quite a good level of stability, and they have good documentation and good support. So you could access some of their models as well if you don't want to go the OpenAI route.
Great. Well, Laura and Sina, thank you so much for this session. This was great. For everybody watching, if you are interested in diving more into multimodal apps, vision language models, Laura and Sina are running a full day workshop this upcoming Monday. You're really going to get to dive in. You can work with your peers, really dive into this. So I dropped the link right there. And I will, send some more information out about that later today. I'm also going to put in the link to the notebook right here in the chat. I'll also be sending that out via email later today if you registered, and it will be in the video description. There's one more question, Laura and Sina. Do you want to get to it?
Sure.
Grab that one. All right, great. It's a mixture of experts approach sensible for multimodal models such as LLaVA.
I haven't played with mixture of experts before. I know that's how I know GPT and Mistral got their models to be so high performant, but I haven't had a chance to play with this with something like a vision and text-based model.
Yeah, same here. But hopefully that's something that we get some more clarity, and this is something that our team in Fourth Brain is continuously monitoring to bringing into the material that we are covering. But yeah, as of now, we don't have any answer to that yet.
Maybe come on Monday and we can talk about it in more
Yep.
detail.
Yeah.
Great. All right, Laura and Sina, thank you both so much. Thank you everyone for your questions and participation. Check your email later today for the slides, the link to the notebook, and any follow-up resources that we have for you. And have a great rest of your day.
Thank you, everyone, and see you soon. Hope to see you Monday.
Bye.